Hello, everyone. Welcome to the next lecture on our lecture series on GANs. Today, we'll be talking about challenges in training GANs. And let's see what we have. So, as we have discussed in the previous lectures, we are running an AI club to start a career in AI. If you are interested in joining that, on WhatsApp, you can scan this QR code. If you are interested in watching the lectures, like what we provide, you can subscribe us on YouTube. And we are also available on other social media channels. You can go to this link. Students are achieving great success in our community. Uh, so these are a few success stories where students are achieving good rank in competitive exams. They are publishing papers in top tier conferences. They are getting they are getting offers for like higher education, and they are also associating with other professors to actually do good projects. So in this lecture series, we have already completed two, and today is the third one where we will be discussing about challenges in training GANs, and then we will talk about DC GAN, pix-to-pix GAN, and cycle GAN, like all individual GAN applications. Today, let's just see like what are the challenges that we face in training GANs. So today we'll recap the GAN architecture, and then we'll see some challenges that we usually face, and how the stability and convergence problems are resolved in GANs. And also we'll see about mode collapse problem and then interpretability in GANs. Okay. So to give a quick recap, so this is the GANs architecture where the generator is taking latent noise as the input and is generating a fake sample, and then the discriminator says whether it's real or fake. Okay, and simultaneously discriminator also gets the real sample so that it can improve which samples are actually real and which are fake. Okay. So if you want to know more about this, I would suggest to go in the previous lectures and see. So one of the a few things that we should note about the GANs is that like it uses adversarial loss, which is also called as min-max loss in GANs, where the generator minimizes the probability of being caught and the discriminator maximizes it. So that means the same objective function is there, but one tries to minimize it and another tries to maximize it. So that's why it is called as adversarial loss. So it follows alternate training. G and D are trained in turns, allowing each other to improve while keeping the other challenged. So there are a few problems that we face. One is the mode collapse training instability. We'll see in detail of both of them today. To solve these, there are two main things. Wasserstein GAN is there for stable training and gradient penalty to prevent overfitting in D. This is also incorporated in Wasserstein GAN. So before going with the challenges, a quick recap. Like in the GAN architecture, we have training the discriminator first. Why? It's because it gives the generator the useful feedback to learn like what the real data actually looks like, and then the generator actually starts training, and both of the D and G are trained in turns. This was the min-max loss. We also see like how this loss was actually formed. If you want to see like how this is formed and what each component is actually denotes, then I would suggest to go into our previous lecture and see how it is formulated, and like what like all components of this loss function or the objective function corresponds to. So this is actually a good exercise. I would suggest to go into the previous lecture and see like how this is formed. And these are the meanings of it. But like I would just say that like so this is the probability that the discriminator actually maximizes that the input is the probability of the actual input to be very high. That means it should be real. and the probability that the input from the generator should be very low. Okay, so that means it should be fake. So that is what. And minimum is like the same probability the generator actually tries to minimize, and the discriminator tries to maximize it. Okay, so this is the actual min max loss function that the both of them are actually trying to optimize. Okay, so a few challenges that are very common in training GANs. One is the mode collapse, where the generator produces limited variations. So that means it collapses to a few modes instead of covering the whole data distribution. We'll see a few examples in the later slides of this lecture. The training of GANs is highly unstable. So the adversarial process can be hard to balance, sometimes cause D or G to overpower the other one. And the third one is the evaluation, right? So, like let's say if the data is actually generated from the GANs, how to assess that the data generated is actually real. Okay, so assessing GANs is challenging because evaluating the generated quality content quality is subjective and hard to quantify. Okay, so GAN's output quality is hard to quantify, and the evaluation metrics like aren't perfect. Okay, so we'll see like what are the few evaluation metrics are there and how we can actually utilize them. So the training of GANs or the GANs in itself are sensitive to hyperparameters. They are highly sensitive to training parameters like learning rate, which can make the training challenge. So these are the few things, but let's see like the problems in training the GANs. One is firstly the stability of the convergence problem, where uh, like it's actually very difficult to balance the training between D and G. So there are and there are a few things to be done there. And then the second problem is the interpretability. So whatever we are doing in GANs, right, it is generating some content, whether it's text content, images, or whatever, right? It's not interpretable, so we'll see some approaches to make it interpretable as well. And third one is the mode collapse. Okay, the solutions proposed for the stability convergence problems are unrolled GANs or Washington GAN. We'll see both of them. For interpretability, we will see InfoGAN. And for mode collapse, there is mode GAN. I think I would skip it, but I will tell you a few things that are actually done to solve the mode collapse problem. So mode GAN is actually not that difficult, so that's why I have not included it in the slides. But if you guys want it, I will be very happy to include another lecture. So please comment and let me know if you want another lecture for this. Okay, so let's just first start with the unrolled GANs to improve the stability of the convergence problem. So unrolled GANs improve the GAN training by addressing the instability between the generator and the discriminator during training. So why? Because GANs often suffer from issues like vanishing gradient or the mode collapse problem. So where the generator doesn't learn effectively because the discriminator becomes too powerful. Okay, so unrolled GANs came into existence because of this problem, which stabilizes the training process. So the key observation we have here is that it allows the generator to peek ahead at how the discriminator will evolve its decision boundary over time. Okay, so that means in the conventional GAN, the generator takes the feedback at the current instant from the discriminator, but here in the unrolled GAN, it the GAN actually unrolls the discriminator for a few steps in advance, and then the feedback from the discriminator is actually considered at the generator. So the intuition is to stabilize the training by letting the generator look ahead at the future discriminator responses. This foresight helps the generator to learn better and avoid the situation where it's overwhelmed by the discriminator, leading to more stable and effective training. So if you want to see the actual paper behind it, so I would suggest to go into this paper, which I have referred in the bottom of this slide. So let's see like how this foresight is actually coming into the generator and how these things are actually working. I will give you like the fundamental understanding, like how the unrolled GAN actually came into existence and how this look ahead actually benefits the GAN trainer. Okay, so if we like let's just see like how this particular thing actually works. Let's say if we see the original GAN loss, let's say at the generator. So it's the this is the loss that we are actually seeing at the generator. So this is dg of z is the discriminator's probability that the generated sample is real. Okay, so generator tries to minimize it, but the generator, sorry, discriminator tries to minimize it, but the generator tries to maximize it. Okay, so for the minimization, we are minimizing LG, so that's why we have a negative sign here. But in actual, generator actually tries to minimize this log value. The generator tries to maximize this dg of z, meaning it tries to make the fake sample appear real. Okay, so this is what the original GAN actually do. So if you are not getting what I'm saying here, I would suggest to go into the previous lecture where I'm talking about the how these loaves are actually formed up and how they are doing things. Go into the previous lecture and you will see how these things are actually coming into picture. Now, unrolled GANs are uh, proposed where this particular loss function, like let's say where if the discriminator becomes very powerful, the generator tries to not learn good quality data. Okay, good quality, or you can say the diverse samples. So if the generator is more powerful, so if the discriminator is more powerful, generator doesn't learn well. Okay, so the unrolled GANs actually uh, in the unrolled GANs, the generator loss LG is computed by considering multiple iterations of the discriminator's feedback. So, as I said in the previous slide, it actually looks ahead for the discriminator's feedback. Specifically, it involves unrolling the discriminator's response over, let's say, k steps. Okay, this k is a hyperparameter. You can tune it. So, in the unrolled GANs, how this loss function actually changes is so the same quantity is kept as is, but let's say some gamma times will take the feedback for the next case steps as well. So where we actually tries to see like what is the generator's discriminator's response on the generated data. Okay, so here dt represents the discriminator state at the tth time step of unrolling after t iterations of updating the discriminator. So here we are unrolling the discriminator for the k unrolling steps. Okay, lambda is the regularization term to balance the unrolling process. Okay, so this is also a hyperparameter. Okay, so this is a new objective function that is coming into unrolled GANs where the discriminator is actually given unrolled feedback or the feedback look ahead feedback from the generator from the discriminator. Okay, so this is observed that this objective function helps the generator to be more stable. So this is what unrolled GAN actually provides. So this is the intuition behind unrolled GANs, and it actually improves the training process. I would suggest to go into this paper to see more details about it. And this is the only innovation that this paper actually provides. Another approach that actually works very well to stabilize the training process in GANs is the Washington GAN, where so this is also called as WGAN. So WGAN addresses the issue of training instability and vanishing gradients by replacing the traditional GAN loss function with the Washington distance or the Earth movers distance. Okay, so in the previous unrolled GAN, the objective function was kept same. There was no change in the distance or other things, but only the future or the look ahead feedback from the discriminator is considered in the generator's loss. Here we are replacing the traditional GAN loss, the min max loss, with the Washington loss. We'll see how this is actually coming into picture. So WGAN improves the training process by providing a smoother loss landscape and a more reliable gradient signal, which helps in stabilizing the training of GANs. So this Washington distance or Earth movers distance is actually known to be very smooth in terms of the in terms of providing the gradients. So it actually helps in more stable training. Okay, so there is a probability of the Earth movers distance. Here, the intuition is that it provides a smoother, more stable training by using a loss function based on the Washington distance, which avoids vanishing gradients as well. Okay, so here another like intuition that this WGAN also provides is that it uses a critique instead of a discriminator. Okay, and replaces the standard GAN loss with the Wasserstein loss. Optionally uses gradient penalty to enforce one Lipschitz constraint. Okay, we'll see all of these things. If you want to see this paper and how these things are actually working, you can go to this particular paper that I have referred here in this slide. Okay, so let's see how the key innovations are and how it actually works. So the WGAN loss for the generator is actually this, which is mostly the same. The generator aims to maximize the score provided by the critique, making fake samples look more real. Okay, so it is actually the same here. We actually don't call it as a discriminator, but we call it as a critique. Why? I will tell you in a while. The generator is actually the same. It generates a fake sample. The fake sample is actually given to the critique, and then it actually gives the feedback, and the generator considers it. Okay, so this is what the GAN loss, so the generator loss in the WGAN. Okay, which is mostly the same as like what we had in the traditional GAN. So, but here the discriminator is actually changed into critique, and it actually considers a few things that I will be talking about now. The critique's goal is to maximize the difference between its scores on the real samples and the fake samples. Okay, so that means it is actually taking the difference between the how the real samples is actually coming out and how the fake sample is actually coming out, and the difference between them is actually the earth movers distance, and this approximates the Wasserstein distance between the real data distribution and the generated data distribution. Okay, so that means the difference between the two distributions, which is the real data distribution and the generated data distribution, this is actually the Wasserstein distance, and this is the discriminator loss, and this is the feedback that is given to the generator as well. Okay, so let's just see how the critique is actually playing the role. Okay. uh, okay, so these are the few things that this WGAN actually do. This traditional GAN uses a loss function based on Jensen-Shannon divergence, which can cause unstable gradients. As I'm talking about, uh, like that, the challenges in training of GANs, where the Jensen-Shannon divergence was used, it actually creates the unstable gradient, and hence the training was also highly unstable. Okay, but WGAN uses Wasserstein distance, which is more mathematically considered good, and it is more smooth, which it has a better mathematical properties, allowing for a smoother continuous loss or more stable gradients. So when so since it is a more smoother distance, and continuous, and it has stable gradients as well, so the the gradients update that we see in the WGAN is actually more stable. Okay, so which is also found that this when we change this loss function, the GAN training is also more stable. This new loss function ensures that the generator receives meaningful feedback even in situations where the discriminator is not perfect. Okay, reducing the risk of mode collapse and vanishing gradients. Okay, so basically, to some extent, the mode collapse problem is also handled by Wasserstein GAN, but it is not completely handled. But the vanishing gradient problem that we had in the traditional GANs is actually handled at a very with a very good accuracy. Okay, so WGANs are actually helping in that. So here we have a critique. So in the WGAN, the discriminator is replaced by a critique, which outputs a real valued score rather than a probability. Okay, so this is also a one change in the critique. So that's why the name from the discriminator is replaced to the critique. Okay, the critic provides more meaningful feedback since it is no longer constrained to output probabilities between 0 and 1. And it ensures the one Lipschitz continuity constraint, where the WGAN enforces weight clipping. Okay, so for each update, after each update, the weight of the critic are clipped to a fixed range of this and this. Okay, so this weight clipping actually helps in many neural network based models. It is also very common in the reinforcement learning based algorithms as well. But here also in the GANs, this actually seems to be helping a lot. Okay, so these are a few updates that were made in WGAN compared with the traditional GANs, and this actually provides more stable training and more better accuracy, because it actually also helps in the vanishing gradient problems. Okay, so another problem that we saw is the interpretability in the GANs. So for interpretability, InfoGAN was proposed. So InfoGAN focuses on improving the interpretability and control of the latent space in GANs by introducing a mutual information maximization objective. Okay, we'll see what these things are. So GANs often generate high quality images, but the latent space, the input noise vector, is poorly understood. Okay, so that means the input that we are giving to the generator, we don't know what that is, and how that is actually helping to generate the content or the fake content, or whatever image we are generating from the GANs. We don't know how it is generated. Okay, so there is no interpretability. We don't know how this model actually works. So InfoGANs gives this structure to this particular latent vector, allowing control over the generated output. Okay, so we'll see how this is done. So the intuition here is that I make latent space interpretable and controllable by structuring it and maximizing the mutual information. Okay, and so here what we are doing is, the key innovations we are doing is that split the latent vector into random noise, and the structured code. Earlier we had only the random noise, but here we also have a structured code. Okay, so with an additional mutual information term that encourages meaningful feature control. Okay, we'll see how these are actually incorporated into the architecture in the next slide. But if you want to read about InfoGAN in detail, so this is the paper where originally the InfoGAN was proposed in NIPS 2016. So I would suggest to look at this paper as well. Okay, so the motivation behind is that, like, let's say, how can we achieve unsupervised learning of disentangled representation? So let's say these are the representations, right? We don't know how things are actually there. Like, so for example, this is one information, this is another information, but they are entangled with each other. So it's actually very difficult to encode when the information is represented in this complex manner. So let's say this representation is disentangled, it would be more interpretable and easier to apply to the task. So we have the information in a disentangled manner. So we can easily consider, okay, so like we can use this information somewhere, we can use this thing somewhere. It's easy to extract as well. Okay, we know, okay, so these are the three things there. Okay, let's say if we remove the color coding from this particular part, it's very difficult to understand like which information is what. Okay, so because these are actually untangled. So this disentanglement actually helps in interpretability. Okay, so how it is actually done, let's say, from the perspective of representation learning, there are no restrictions on how ZZ uses Z. Okay, but Z can be used in a highly entangled way, and each dimension of Z does not represent any aligned features of the training data. Okay, so let's say this is particular part of the data distribution, and the generator actually uses it to, let's say, generate, let's say, one. Okay, and this particular data is actually used to generate, let's say, number three. Okay, we don't know, but these are entangled in some way. Let's say if we somehow can make it disentangled, we know that, okay, so one particular part of the input actually, okay, generates the one particular part generates three, and so this is how the generation process is actually working. Okay, so the idea is to actually make the information disentangled. Okay, so how we do it in the InfoGAN, the key innovations that we have here is that InfoGAN modifies the traditional GAN by introducing an additional term to encourage the disentanglement and interpretability in the generator's latent space. Okay, so what it do is, so this generator earlier had only one input, the Z, but here we have C as well. So this Z is the noise vector and C is the additional structured latent content that represents specific feature of the generated sample. Okay, so what we have here is we have the generated noise, and we also have a latent space. So for example, let's say if we are, let's say, generating faces. Okay, so C can represent that, okay, so this the face should have the specs, the face should have, let's say, maybe white hairs, the face should have black hairs. Okay, so this kind of representation of the features of the data should be there. Okay, and then this is given as the input to the generator, and then correspondingly one output or the fake image is generated. Okay, another core innovation in the InfoGAN is the introduction of the second loss term called the mutual information loss. Okay, so here this is the second loss term introduced. It is called as a mutual information loss, which encourages the generator to map a specific latent variable to specific interpretable feature of the generated sample. Okay, so this latent code is actually considered as the uh, like as one particular part of this loss function, and which helps to like generate the specific feature in the uh, in the discriminators out. Okay, so this mutual information loss, so this info gain maximizes the mutual information between the generated uh, structured latent. Okay, so this is latent code C and the generated sample G. Okay, so this is latent structure that we are actually proposing, this G Z of C, and the C like we are considering the mutual information loss, and then this is given as a feedback to the discriminator. Okay, additionally, there is another auxiliary network queue as well. I will tell you about that in the next slide. So if we see like what InfoGAN actually does is it actually transforms the original random noise vector Z into two parts. One is the unstructured noise Z. So this is what we had in the traditional GAN as well, which provides variability to the generated samples. And structured latent code C, this is a discrete and or continuous variable that controls specific interpretable attribute of the output. Okay, so like rotation, color, scale, or some particular feature of the feature in the generated data. The generator is modified to take this both Z and C. The goal is for C to control specific feature of the generated output, such as the position, shape, color, object, or whatever, right? The InfoGAN introduces an additional auxiliary network queue that approximates the posterior probability of C, which helps the model learn the relationship between C and the generated output. Okay, so this auxiliary network is trained to maximize the mutual information between the structured latent code C and the generated sample. Okay, so this is how the InfoGAN actually is different from the traditional GAN loss. Just hello, yes, बताइए. नहीं चाहिए भैया, नहीं चाहिए. Okay, so this is how the InfoGAN is different from the traditional GAN. In the conventional GAN, generated data X does not have any have much information on the noise Z from which X is generated. Okay, because the informations are highly entangled. But here in the InfoGAN, we provide the specific attribute like which makes the information specific. Okay, so we give this C as the input to the generator, and this is how the objective of the GANs is actually modified. This is the traditional GAN loss, and this minus lambda times the mutual information between the like between the code C and the generated out. Okay, so this is how the mutual information loss is actually incorporated. This is the mutual information I between the latent code C and the generated data X. Okay, so this is how the things are actually modified in the InfoGAN. Okay, so this is the mutual information. I think I will not go into the detail. Like, so if you guys have any query about it, if you want to understand it, please comment. I will give you the explanation of how this actually is incorporated. Basically, the entropy of the prior and the poster distribution is actually incorporated here. This is very simple to understand. You can do that. Okay, so another thing is the mode collapse. I will not include the explanation to the mode GAN because it is very simple. As I have explained, like how InfoGAN, WGAN, or Unrolled GAN actually like makes changes uh, uh, to the GAN architecture. The mode GAN is also very simple. So mode collapse is actually a very common problem where let's say consider an example. I would like to use GAN to produce faces like the one below from NVIDIA, right? So these are the two faces, ELA and let's say Keras. So these are the two faces. I want to generate data from these two distributions, but my generator actually somehow finds one image that fools the discriminator. Okay, this looks like a real image. A discriminator says that okay, it's real, it's real. Generator says that oh, I fooled the discriminator, and it actually doesn't do anything. It only produces this particular image. So what happens is generator could then just produce that image every time independently of the input noise. Okay, whatever input you provide, the same output is actually generated. So generator actually fools the discriminator, and generator is indeed fooled. So the discriminator is indeed fooled, and but the generator is not doing anything good. Okay, so the problem here is that the every sample made by the generator is identical. Okay, so this is mode collapse. Okay, so instead of actually generating data from the all the modes of the data distribution, it is only focusing on one particular mode, or maybe let's say one particular image. Okay, instead of one image, let's say maybe some variations of this particular image is only generated. Okay, that is also kind of mode collapse only. Okay, the challenges is that it's much more common when the system produces the same few outputs, the minor variations of them. This is called as partial mode collapse. Okay, then some variations of one particular image only. The solution is to extend the loss function with an additional term to measure the diversity of the output produced. If the outputs are all same or nearly the same, the discriminator can assign a larger error uh, to the result of this particular sample. Okay, the generator will diversify because that action will reduce there. Okay, or we can use the WGAN. Gaussian GAN also like helps in mode collapse problem. So that's why I have not included mode GAN here. Mode GAN is also somewhat similar. You can see the paper and things are there. Okay, so this is how the mode collapse problem is actually addressed. So let's say a few other things that can be done to address the mode collapse problem. You should diversify the regularization technique, mini batch discrimination basically enhances the diversity by comparing samples uh, within the mini batch. The feature matching adjusts the generator training by matching intermediate layer activations to stabilize the learning. One-sided label smoothing is also done, where it decreases the discriminator's confidence in predictions, encouraging generator to explore more diverse outputs. Or we can also do we can also add the noise into the input. So let's say injecting noise into the input space to diversify generated samples prevent collapses to the single mode. So this is a very common or maybe very common solution to the problems when you see like this the kind of same output every time in the neural networks, not only with the GANs but also other kind of neural networks. Like this is the solution, one of the solution that you should try. The more diverse input you give, the output of the neural network is tend to be more diverse as well. Okay, so adding noise actually helps. Okay, some real examples that the GANs have actually proposed. Just see, right? A few of the faces are very real, but a few others are actually, let's say, just see, these are let's see, right? These are like ghost faces. Okay, but these were the outputs from the like few initial few GANs paper. Okay, but I will say like how is it that you can actually generate the original faces in the next lecture, where I will be giving you the code of DC GAN. Okay, so another thing was the evaluation matrix. So one common thing is that like there are two trade-offs here. One is the quality of the images. How is it that you will say that the generated images are good in quality? Another is the diversity, right? How will you ensure that the generated output is diverse enough? Okay, so there are two common metrics used. One is the inception score and another is Fetch's inception distance that are common used to assess the quality and the diversity of the GANs output. Okay, so these are the two common matrices, but it depends highly on the applications. Okay, so for your application, it could be some other metric as well. Okay, so the real world impact of GANs is that the data augmentations for small data sets revolutionize creative industries and enabling new scientific research applications. So this is the positive impact that is actually coming from the GANs, like mostly in the research community. And the negative impact, I think you must have seen the news from the deepfakes that the criminals are actually using the GAN-based technology or the Gen AI based technology to actually fool the customers, fool the innocent people, and so on, right? So there are some ethical concerns that these technologies are generating, and the potential misuse of these methods is actually very bad, and it also spreads misinformation. So the current mitigations is to address how the AI community is developing detection models and ethical guidelines. So one of the common solution is coming from the regulation side, where let's say if you are a developer, you have to follow those regulations in making these models public. Okay, so the future directions is to improve training stability. So there are so many other things are done. So like spectral normalization. So there is a lot of ethical research going on to discuss emerging research on responsible GAN usage and detection of GAN generated content. And new architectures are actually getting proposed. So including hybrid GAN based architectures, like for various applications like medical imaging and robotics. So these are a few things. Let's just like this was the like thank you for attending this lecture. See you in the fourth lecture. Sorry, not the third lecture. See you in the fourth lecture on DC GANs. So this is I think we are done for today's session. Sorry for it. So this will be the fourth lecture on DC GANs. Okay, so where we will be talking about like how DC can actually generate the images. I think these are the very bad images, but DC can actually generates very good quality images. If you are interested in our AI community, please join this WhatsApp group and like stay tuned. We'll be coming up with more sessions as well. Thank you.